actually had, maybe 25 years of human spaceflight experience. So kind of a mix of science and human spaceflight, which has been really wonderful. About 3 years ago, I was asked to co-lead an effort to select where the human base that NASA would be primarily leading on Mars. And I'll talk to that a little bit, but one of the themes that you see there is the importance of water. I mean, we all sort of take it for granted on this planet, but on Mars, I would say that's become a major issue, because for a long time we didn't think there was water on Mars, and now we actually know there's substantial quantities of water. And so there's a very interesting set of trades that need to be done to figure out where that water is and where it's accessible and what it takes to produce it. And I hopefully can give you a sense of some of the work that's being done. But what before I even get into it, I would make two comments. One, we're living in an incredibly exciting period of time. I mean, I think personally that 1,000 years from now, they'll look back on here and they'll say, this is when they became a multiplanetary species. And there's confusion, there's lots of things we don't know, but in the end, I think that's actually what's happening right now. And then I would like to talk a little bit about the things we don't know, because when I try to tell you what we have learned so far, the category of things we don't know is much, much bigger than the things we know. And really, by working together, I think we can really figure out those answers. And it's not just PhDs or people with tons of experience. I actually liken Mars right now to being like the internet was 25 or 30 years ago, where if you have a drive and a determination to learn and contribute and find things out, regardless of whether it's a space agency that's never attempted to do that, or if it's a student in a university, the opportunities to contribute are massive. And there are really wonderful opportunities here. And I'm going to try to give you a little bit of them from the water perspective, but they exist across all the spectrums right now, whether it be entry, descent, and landing, or how you launch off of Mars, and so forth. But this one in particular, I think, is really fun for me, as is. And as we go along, if you have questions, I don't know if we have a mic, but if we have questions, it's really nice to actually be able to take them while we're talking, so it's fresh in your mind, because it'll give me ideas too. Okay. So I love this picture because the movie The Martian was fantastic. It is as close as NASA actually worked very closely with the movie producer and even the author of the book, and it is probably as accurate of a depiction, if you will, of how a Mars base would currently operate as we would envision, with maybe some without the drama. But the point being is that actually, to some extent, I believe that Mars doing things like this helps people visualize it and start putting the pieces together. And so I love to start it out with this. And for NASA and for many space agencies, including the UAE, the vision of Mars is this pulling vision that is really galvanizing a tremendous amount of energy. And you see it all across the board, and it's really cool. And so it is our long-term goal. I fully anticipate work being done in cislunar space and even potentially on the surface of the moon, but with an aim towards enabling Mars. So about 3 years ago, we started an effort to start finding out where we should put the base on Mars. So you say, well, if that's 15 years from now, why are we doing it right now? Well, there are a number of reasons, and I tried to outline those right here. And the landing site we call an exploration zone, at least at NASA. And the reason being is that we're assuming that you land in a central area and that you have a 100 or 200 kilometer diameter circle with rovers that you can actually reach at with human crews. And so when we made a call for these landing sites, we were looking for cool science, diverse science. We actually prioritized science objectives as best we knew them. We're having a human beings there, and could give us the maximum bang for the whatever currency in terms of science returned. And so, for example, looking for life. We've attempted to do it with robots. But it's like right at the top of the heap, because when you put a human astrobiologist on the surface of Mars with her equipment right there with her, the amount of science that we will be able to do is tremendous. And so, for example, with the Opportunity rover, about 2 years ago, we crossed the marathon mark, which means we had gone 26.2 miles in 10 years with that rover. On Apollo 17, they basically did the same distance in 3 days, because we weren't trying to talk over time delays and everything, and they were able to cover a tremendous amount of ground. And there is a bit of a correlation between how much distance you cover and what you can find. And so that is one of the ways you see that having a human being there is massively helpful in terms of pushing the science envelope. So in these explorations, so we were looking for this prioritized science objectives, and then we were also looking for resources. And I would say that what you will see coming out of this talk here is that the central resource that we feel collectively that we need to know more is water. And that probably, I would even go so far as to say, as a co-lead for this effort, drives base location. Okay. So the other thing is that the reason we wanted to start now, we have amazing assets. I'll show you there. When I say we, I'm talking the human species has amazing assets at Mars right now. And it's not a well-known fact, but we've actually been exploring Mars with our robots for 50 years, which is really incredible to think about. And there is a fleet there now that is absolutely incredible, and I'll show you a picture of it. But so many of those things, particularly our Mars Reconnaissance Orbiter, is getting pretty old, and we wanted to start actually using those assets to start identifying where, to fill in the gaps of where, about these different sites that are being considered. The next thing is that the last point, I'm not going to, the first one, obviously you get a database of sites. And I should say one thing. We had 47 sites proposed by all people all over this planet. I think we've gotten so smart that on the next time we do a call, which I'm expecting within the year, I'm actually hoping for 100 sites. Because I think we are so much smarter, and that if you apply all that intelligence and creativity to a tighter set of criteria, what we will find is amazing. And then lastly, the reconnaissance. What we have done is, so for example, Mars Reconnaissance Observatory, it has a radar on it. Well, when it was launched, we thought that Mars, if it had any water, would actually be deep aquifers. And so the radar that we use has frequency ranges that were designed to look for deep aquifers. Unfortunately, when we got there, we found something like happens on a frontier all the time. We actually found something we didn't even expect, which is whole buried oceans and glaciers on the planet that are literally covered with dirt or regolith layer that no one expected. And unfortunately, it has a noise range, the way it is, that you can't really see the ice in the first 0 to 10 meters, which for using it for drilling is exactly where you want to be. So there is a massive hole in terms of our knowledge of where that ice is that we really have to go fill in. But that's an example of where it's teaching us about reconnaissance that we really need to go after. Any questions so far? Okay, moving on. This is the fleet. Well, there's a couple errors here on this one, but I could, unfortunately, they don't let us travel with our real laptops. I couldn't fix it. But you can see that there's a tremendous amount of assets that are there. And again, those are not just NASA assets. So you see the ESA, Trace Gas Orbiter. You've got ISRO, you've got MAVEN, which, and you've got Mars Reconnaissance Observatory Orbiter. So, and then you've got Curiosity and Opportunity there. InSight's launching this year. And then you can see the UAE's HOPE mission coming up, the MMX, which is an incredible mission by the Japanese to actually land on Phobos, or dock with it would be a better way to say it, and actually bring samples back from the Martian system to Earth. The first time that has ever happened, which will be really pretty fascinating. And then you can see the 2020 rover, which is hopefully the beginning of a campaign to actually get samples back from Mars. And then the Chinese are also heading there as well. Let's see. The first landing site was in October of 2015. Angel, who's sitting right there, was there too. And we had 400 participants in this thing, and they were literally, as I said before, from all over this planet. We had proposals that were even coming in from the Ukraine, for example, in terms of potential sites. Let's see. And the next page I'm going to show you, actually I'll go back if I can do it. Those little dots there, it's not the best way to see it. You will see every little circle there is actually a proposed landing site on Mars. And we had purposely opened up the range that we were looking for to be plus or minus 50 degrees latitude, because we really didn't want to collapse the trade space down too much. But these sites were coming in, and everybody, it was astounding how much work went into developing those sites. Go forward. And so, let's see, there was strong agreement on this exploration zone concept, and then really the big thing here is that there was strong agreement about water, which is really where I'm trying to go with this. There's exploration zone, we already kind of talked that, but what you're looking for across that 200 kilometers is amazing, diverse science that takes maximum advantage of the human being there, and also resources with water being the primary one. I'd love to show this slide because it's actually, we brought a version that everyone could sign, and the energy about going to Mars took me by surprise in terms of everyone's desire to sign that thing. And that gives you a sense of what we're all attempting to do, I always feel. Okay, so. And just a brief few slides about the importance of the concept of an exploration zone, because that's, and needing access to resources. I would suggest that across the entire history of exploration, we have learned that picking a site well really sets you up for success going forward. And so in Antarctica, for example, the McMurdo station really started out as a hut originally, but it was well chosen. It had access to the water. It was just a well-chosen place, and it has literally, down in this lower right-hand corner, grown into a city or a town that actually requires urban planning now. And it is where everything funnels in to head out to the research locations in Antarctica. Historically, I'm not going to go through these, but you have a number of examples. Jamestown in the United States was actually a poorly chosen place, but then you have Quebec City, and I would even argue the International Space Station, per what Chris Hadfield was saying, are well-chosen locations, and they have really worked well, and they teach us a lot about how to choose a site. Now, let's talk a little bit about here, because what we're really talking about is in the far left-hand corner of the site that's there. But really, the whole reason on water really is tied to the fact that, and you'll see in a moment, the biggest thing we need water for is the Mars ascent vehicle. It's the cruise ride home. And the reason being is that that rocket that sits on Mars actually needs propellant. And if you use oxygen as an oxidizer and you use methane, you can actually produce in time all of that at Mars. And in fact, even the very first use of a Mars ascent vehicle, we're planning on using the oxygen. And the reason is this: it's about the current landers that are assumed to weigh about 20 metric tons. So to give you a perspective, Curiosity, which landed, was 1 metric ton. These, the landers that we're talking about, and with the Mars ascent, are about 20 metric tons. And these are big spacecraft that take a lot of propellant, particularly for that Mars ascent vehicle, to launch. So the oxygen alone is about 28 metric tons of oxygen. If you send that all the way from that wonderful blue ball that we call home, or low Earth orbit around it, all the way to Mars, you can take that 28 metric tons and multiply it by 10. And that's how much propellant it takes to move that stuff all the way from Earth, all the way to the surface of Mars, roughly speaking, which is a massive number and actually requires a lot of capability. So the trick, and you'll see these numbers in a moment, is to produce it locally. So that's the oxygen. The other piece is the fuel, which would be methane. And the beauty there is we now know there's tons of water. We'll talk about that in a little more detail. And the water gives you the oxygen, or the hydrogen, and then you've got carbon dioxide in the atmosphere, so that's for your carbons, so you can produce the methane that way. And so that is incredibly powerful. And that means that's another 8 metric tons you don't have to send from low Earth orbit or from the Earth all the way to Mars. And the economics of that really starts driving everything. Any questions so far? Okay. All right, so this is sort of a self-evident thing. I love this one from the American West. It's kind of a joke, but if you actually try to explore anywhere with the way that we are currently doing spacecraft operations, it's insane. We have to learn to live off the land, and that's actually this fueling of the Mars ascent vehicle is probably the first immediate use and dramatic use of local resources. Okay, so this sort of talks through a number of pieces of this, but you can see that the Mars Ascent Vehicle, we were kind of already talked this. The big thing is oxygen first, because that's at 28 metric tons. That's the big prize. And the beauty about oxygen is we know the Martian atmosphere is carbon dioxide, and we know how to extract oxygen from the atmosphere if you've got power. So that one's a no-brainer in terms of doing it. The tricky part is that you have a lander that has been pre-placed on the planet probably years before a crew gets there, and that you got to make sure the production of the oxygen and the storage of it and the machine keeps working across years of dormancy at Mars, which is no mean feat in of itself, but it is an engineering problem that we will figure out collectively. And on the Mars 2020 rover, we actually have an experiment called MOXIE, which is the first time that we are actually producing oxygen at Mars. It's a fairly simple experiment. There will need to be successors, I believe, that are actually not doing a more full-scale production and storage and maintaining it, because storing it in the Martian environment is not trivial in and of itself. Any questions so far? Okay. Then you go after the water for the feedstock. And I love this picture because it was just released literally about 2 weeks ago. So we know that there's water there. Well, there's several reasons we know it, because we have the radar. There's a noise range where we can't see it, but we know it's deep and it runs deep, because these were literally oceans. Mars actually looked like the Earth in its early period. So it has the oceans and it had glaciers. And so, but we have, you can either use a radar, it tells us that it runs deep, but there's that noise region right there. And then secondly, we have, we can actually see hydrogen signatures off the surface. And so you sort of infer from all that that the water's there and close. We've actually on Phoenix scooped up and seen ice. We've seen we've seen meteorites hit Mars, and then when it hits it, we actually can see it. It strips the dirt or regolith away, and you see pure white ice right there. And then the atmosphere is so thin that it evaporates, and then it goes away. But we see that. This picture that was just released is cool because it's an escarpment where you've had a collapse there, and you are seeing pure water ice right there, a whole layer of it right there, and it is just begging to be used. And it is, and that, to give you a sense of that, if you put the SLS, the big heavy lift rocket that the US is developing, it wouldn't even fill that up. It's that thick of a chunk of ice. And just to give you a sense of how cool this is, if life exists on Mars, it's probably close to the water. And so we now know, and then also there's growing belief in the astrobiology community that you need to get below the surface somewhat so that you're away from the radiation environment. So not only is it important for in situ resource utilization or utilizing it for humans operations, but it's actually where the science is too. So it's really neat that you start to see these things. Yeah.
If there's a dust storm or there's a lot of dust in the air, would that be a problem if you're trying to make, propellant or whatever from the atmosphere?
So it's a great question about dust storms. So dust storms, so first of all, on the movie The Martian was not correct. Not that you're saying this. It was not correct about dust storms. They do not have that much force associated with them, is the bottom line. Dust storms they occur periodically. They actually can engulf the entire planet. And so they are a problem, but they don't really stop us with our rover operations, and I don't expect them to stop us here. If we are using solar power initially, because we don't have nuclear fission yet, and that's a possibility, dust storms are problematic because what they do is they can attenuate the light so much that your power production drops off dramatically. But fortunately, they don't happen very much, and also they happen mostly, even when they're not global, they happen mostly in the southern hemisphere, and we're still trying to understand that dynamic. Yeah?
You mentioned that when the ice is exposed, it evaporates. Are there any pockets along the strata where there's liquid water, where the temperature allows that?
Yeah, so the question is, are there any places near the surface, right, where there's liquid water? No, there really are not. We have not found any. The problem is that Mars is so cold. On a warm day at the equator, it'll get a little above freezing, and then at night the temperature drops 120 degrees. And so the atmosphere is so thin. It's like being at about 110,000 feet on our planet. So if any ice shows up, it'll actually sublimate straight into the atmosphere right away. And I'll talk a little more about that because we're getting smarter about the buried ice and how we might get it, which ties directly to your point in a moment. Yeah.
I had a question basically that you can talk to at the end.
Okay.
Is how much of this can be accelerated or facilitated with more resources and funding?
Let me come back to that. Okay. Yeah. No, it's a great question, and how much of it can be done in parallel too, right? Because there is serialities here too that I'll try to allude to, but that's a fun question. Okay. So the Mars Ascent Vehicle is the big one, but if you're looking towards a sustained presence, then there are lots of other reasons why you need water. And so, for example, the 2117 vision that the UAE is putting out, or that SpaceX, for example, has a similar type of vision, those are very exciting because what they do is they help the community start to realize just how much water you really need. And I believe that actually provides clarity as you go forward. And I'll try to allude to it because if you're looking towards a more sustained presence, then you start worrying about oxygen and water for the habitat and laboratory. Eventually you're looking at the topic that came up just beforehand, which is farming. And whether it's hydroponics or just farming, that's a lot of water. And you're not going to be able to bring it all the way from the Earth. And then similarly, these rovers, the rovers are fascinating because that actually, my personal belief is that is what we may use on Mars first. Because if you land in the wrong place, the beauty about a rover is it can come to you. A habit laboratory cannot come to you. And so I suspect that as we get further into the mechanics of actually executing this, we'll realize the importance of these rovers. But rovers, compact power source is very important. And so if you have oxygen and hydrogen, you've dissociated them, you can actually run fuel cells, which generate electricity. So that water can be used to actually generate power for a rover and gives it mobility. So that is a very powerful use of water. I'm not going to go into this chart, but the bottom line, it basically says that for a Mars Ascent Vehicle, a lot of eye charts here, but basically you need about 28 metric tons of oxygen, and you need about 8 metric tons of water, and that's a lot, or methane, and you need a lot of water to produce the methane. And so that's really all that's saying. Now, let's talk a little bit about the types of water. There's basically two broad categories of water feedstocks, if you will, on Mars. There's what we call hydrated minerals, which are basically minerals where the water molecules, or there's a lot of water molecules locked up in the mineral, okay? And so that is what we have historically, at least at my agency, have viewed as the primary source of water. It's only been within the last 10 years that we found those oceans and glaciers. And so now the thinking is changing. We're still looking at both of them. And so you see these debris-covered glaciers. And then there's really, further north, you have basically whole, what we believe were oceans that are now covered. In fact, Mars slowly outgasses, but we believe, roughly speaking, about 18% of the original oceans are still present on Mars, frozen, billion-year-old frozen water feedstocks. And so those are the two. Now, and I'll talk a little bit about them. So the idea behind hydrated minerals, to use that expression, is that you basically go and scoop them up, and then you bake them, and then you free the water molecules out of them, and then you collect the water. Now, the challenge there is that we don't do that anywhere on this planet that I'm aware of, and because it's very energy intensive to do that. And so, it sort of stretches the imagination to imagine doing it at Mars where you're extremely energy deprived. It's all an energy game. And so those have a problem. And the other problem is that you have to scoop up dirt all the time. You're literally going out, many of these concepts, it's 3 times a day, doing it, and there's no human being there. And anyone who runs a mining operation will tell you that that stuff breaks all the time, and on this planet we send people out and fix it. So the idea, there is a bit of a challenge there. The buried ice one, that's where really a lot of the thinking is needed right now, I believe, because that ice is probably within a meter or two of the surface in some of these northern latitudes, and you can get at it. And what's fascinating is that in Antarctica right now, that is actually how they get their large quantities of drinking water. They build what they call a Rodriguez well, where they drill down through it. And so this is literally, we've been trying to apply this to Mars over the last 2 years, and we're really getting very excited about it. Because the big problem at Mars, we originally thought you just go in and bulldoze it off, scoop it up, get the dirt layer off, if you will, and then go in and drill the ice. The problem is that sublimation issue starts coming in. At Mars, what they do in Antarctica may be perfect for Mars, because you basically are using Mars as it is, not as you want it to be. And you're leaving the dirt on top of it, and maybe even an ice layer there, and then you're developing a pool of water underneath there. And that way you are literally protecting the water pool down there from the Martian conditions by having its own layer on there. It's also useful for another reason, which is that we don't really understand the dirt, and we're going to have very limited opportunities to actually go check it out before we actually are banking a crew's life on it. So making sure the beauty of that is that if you can get through the dirt, then you're home free. We know how to melt it. Any questions about this one so far? Yeah.
Hi, my name's Andrew Barden.
Hey.
I'm from Quebec City, so I was very happy to see that if you can survive Quebec City, you can survive Mars. On Earth, water is part of cycle. Do you have any ideas or any theories as to whether the same thing there? I mean, is it locked and has been that way, or is it dynamic?
It's
and
dynamic.
Something going on that we're not seeing?
Yeah, it's dynamic, and that's actually an area of research that is very current right now, and a lot of homework needs to be done on it. We do know that there are cycles. And there are winters. Mars actually, and the winters can be very severe on Mars, and where they're depositing snow in the terms of water, and they're depositing carbon dioxide. Carbon dioxide freezes out, and you can get significant layers. And so that there is what we call a hydrosphere on Mars, but we don't, which is really what you're referring to here on this planet. It's not as dynamic as the one here is on Earth, but it is definitely dynamic. In fact, some of those, in that picture here, let me go back, there is strong belief that there are mechanisms that are depositing even more ice there sometimes in those layers. And we don't really totally understand those dynamics right now, but that's actually an area where there's a lot of opportunity for research to fully understand that mechanism. But we do know it changes, and we definitely know that it snows both water, snow, and carbon dioxide. Yes, so the temperature at Mars, it depends on latitude, like this planet. Down at the equator, it can get up to freezing, a little above freezing. And then at night, because the atmosphere is so thin, it'll drop 120 degrees. And so there's an enormous temperature swing. And then you go further north, and it gets challenging, particularly near the poles. And so this ice that we're talking about is, we really want that if we're going to go after the ice, you want to be as far south as possible, because it's just thermally much easier. It's easier on the machines, easier on the people, and that kind of thing. So really finding where that ice is and trying to find it as far south as possible is the whole game in terms of figuring out where a base goes and trying to make sure there's amazing science to do too. Did I answer your question? Okay, cool. All right, so feedstocks. All right, so this really, so whether or not you're using hydrated minerals or whether or not you're using subsurface ice, it really rotates on 4 questions in my mind. First of all is a concept of how much water you're using, right? If you're only going one time or a few times, you can sort of take a shortcut and not even worry about water and that kind of thing. But I think all of us in this room are aiming for something much bigger. And if you're aiming for something much bigger, then you really have to get down to how much water does that equal. And I think that, like, for example, in the UAE 2117 vision, not to focus on that too much, but that's a lot of water. There's a tremendous amount of water. The SpaceX one is a similar one. And so, and if you start doing multiple crews, even in the beginning phases, where you're starting to introduce agriculture, that's a lot of water. And that probably shifts you towards subsurface ice. So there's that question. And the next one, is it really there? Okay, so everything I am telling you right now is based off of orbital measurements. So the hydrated minerals, for example, we can see with using spectrometers, we can actually, the light that bounces back, we can actually see what minerals are down there. And so we know that there are hydrated minerals, these fields of these things, but we don't really know their fields. They could be a vein. The resolution in those spectrometers is wide area, so if there's anything in there triggering it, it could do it. So we actually sent Curiosity after one of these things to look for the hydrated minerals, and we could not find it. And so that's alarming, because if it could be that there's just a vein that's running, and then the area is so wide that we're looking at, that vein's triggering the signature that it's there, and then you go to find it and you can't find it. So that's one challenge. And then on the subsurface ice, there is this issue of this area, this 0 to 10 meters that we just don't know about. We were doing everything we can to actually close that gap, but it's probably going to take another orbiter to do it. But closing it's key, because you do not want to be deep drilling for these first missions at Mars, because there's just too many unknowns to really be doing that. Any questions so far? Yes, Chris.
Rick, can you clarify how the capabilities for detecting water and extracting water on Mars might actually be beneficial to people on Earth? Can we utilize this technology here in arid areas on this planet?
So I think we can't, let me put it this way. This is an extreme environment, right? And so when you start to deal with trying to find something from orbital sensors, right? That's one area where I think we're going to learn a lot. Because normally, if you're in the oil and gas industry, they hardly even use orbital data. They usually have drones and aerial things, and then they start doing there's a whole sequence, but it usually starts from down low and actually trying to identify it. We are trying to go straight from orbital to a landed mission on something that costs billions of dollars, and you kind of are forced into that. And I think that extreme technology case will actually teach us a lot about how to do that on this planet. Producing water there will be challenging too, and so it's going to push a lot of things, including the equipment that's producing it, that I am absolutely convinced will have ramifications for this planet as well. It's like, for example, the habitat. Let's take the habitat for a moment. It is under such extreme things. You're trying to make that closed loop and everything. You can do that here on this planet. But when you have no choice, but you have to do it, you actually go the extra yard, and that will have immediate ramifications back here on this planet as well. So I'll give you one more, not that it's tied to water, but this is another example. Solar cells. Mars is basically 100 million miles further away from the sun than the Earth is. And so we're probably going to be using solar cells. So we are going to have to make them work much better than they do on this planet, because the intensity of the radiation drops off with 1 over r squared. And so it's a long way. And so meeting that design challenge is another example of how it'll have dramatic impacts back at this planet in terms of the efficiency of our solar cells. So those are just some examples, but the bottom line is that these extreme engineering environments really force us to innovate in ways, and I'm absolutely convinced that the water discoveries mechanisms and production mechanisms will have ramifications back here. But I'm not sure we totally understand it yet. Yeah.
Could you say a little bit more about hydrogen in the H2O in terms of your ability to convert that to energy and store it as an energy opportunity out of water?
Yeah. So energy is the name of the game. We at NASA, we've actually just done, we're actually in the midway on a study where we're looking at all the major challenges for getting humans on the planet, so that we get really track them and make sure we're progressing. And surface power is a big one. And so really, I think the entire community has converged that we need compact nuclear fission reactors, and so, but complemented by other power sources like solar and something called radioisotope thermal generators, which are basically decaying plutonium. That is a very known technology, and it's a poor electric source, but it's an amazing heat source. And for labs, we may need that heat source. So a mixed fleet is a good thing. But in general, what's going on there is that you're probably using nuclear fission. using that power that's generated to actually break apart the oxygen and the hydrogen, and it's essentially storing the power from the nuclear power plant. And putting it in the rover so it can then use it later on. So it's essentially an energy storage mechanism. But the original energy came from the fission reactor. Speaking of which, we actually just did a test 2 weeks ago where we have a fission reactor that's about the size, like about this big. I mean, it is amazing, and that technology is coming along dramatically. So let me just finish this slide. I think we've pretty much covered everything. Can you produce it economically? And so that's getting at, can you go out and actually produce from the hydrated minerals, or can you do it with the subsurface ice? And then the last thing is, and this question we've actually gotten smarter in the last two years, which is that, it's not even about landing. We know you can land in these sites, but if you have to go to more northern latitudes, the question is, can you launch off of there? Because you are producing all that energy in terms of storing propellants, and that vehicle is going to be very energy starved, and it has to rendezvous with a mothership called the Mars Transfer Vehicle, and that's pretty high up there. And so we need to really go study that to make sure that we can get off those kind of locations and rendezvous with it. And so there's a trade space there, and I think that may be a good stopping. So let me just quickly, and it says what we're doing to solve this problem. Those are the sites, and this is really the key thing. And I cannot tell you how much I mean this from the work that I've seen. No one has all the answers. By working together, we can totally crack these problems. I'm absolutely convinced of it. And but it requires the kind of collaborations that, for example, May talked about, where you get everyone really trying to figure out the problem and doing it. And I am absolutely convinced that we will be able to solve the water problem and a lot of other problems by doing it. And then sooner or later, we'll have a human being there seeing a sunrise at Mars that looks like that, which is totally incredible. And I love how small that sun is. That's what an extra 100 million miles does for you. Okay, thank you all very much.